Okay, in today's video I would like give a short tutorial on how to simulate a tensile test with this result, something like this. This is not realistic, but the point is how to construct from scratch to the post processing until we got stress strain data. First of all, we're going to download the specimen computer aided design. I recommend you to use the CAD from Amintofa and download this file. You just create account, or I have the account, so I logging it and I download the file as fast as possible, and then I import this file to the ls prepost, and I will save it in the geometry. Download. Okay, after I download it, I the extract here, just replace it because I just try it and it is not working, so I download it again to make sure the specimen can work very well. So open your new Windows of ls prepost and then open and import the Icast file from file import Icast file, and you choose the extracted geometry Icast file and open it up, and you can specify the centimeter or anything. I recommend you to, yeah, because the specimen I think in centimeter, so you have to scale up to one, yeah, 10 times, yeah, 10 times, because I mean of make the cat in centimeter units. So in my case I will use kilogram, millimeter, millisecond, and GPA, and also, yeah, the consistent units in ls DYNA. Just click OK. You can also scale it up and scale it down after you mesh it, so no worry about the how you import the Icast file. So first step, just import it, and then the second step, you mesh your geometry using auto mesh here, auto measure, and you select the geometry, just select the face, and then you try this default 0.1. This is so small. Try with 1 maybe, or compute to see the suggestion. I try to make 2 millimeter, for example, and I click mesh, just jump it and click the mesh, and the results is quite a long time, because maybe this is too short, yeah, too small, and it will take a lot of time, depend on your computer. So this is so small, this is so small, just reject it and try to make maybe 10. Okay, it is better now. 10 accept. Okay, in here you can measure the overall length. Select the nodes in the edges, and oh, this is so long. It is impossible. The specimen of tensile test have 1650 millimeter, This is impossible, so you have to scale down by using the transformation here. Transform by using scale in x, y, z direction. It means all the direction must be shrink down or shrink up with the scale factor, for example 10, and you pick the origin. Just pick the origin is default 0, 0, 0, and select the part and scale down. Okay, just click OK and hide the shape geometry, and you now can remeasure the edges. This and this is 155. This is quite realistic and this is good. Now this is the first step. Second step, you create the boundary condition by selecting the nodes for single point constraint here, SPC. I love this. I love to use this because this is so simple. Boundary SPC and create, and for example here I will make it fixed. Select area, select nodes, so select this and apply. And the second in the right side I will make it move, so I have to make set nodes here. Set nodes means we define we define nodes for whether for movement, velocity, or prescribed motion, whatever you want. Just create move parts here. Select the nodes. We'll select this and apply. Okay, then. And then the velocity must be defined in the, this is a quasi static tensile test, so you have to define using boundary and prescribe motion set, that is prescribed rigid motion rigid. It means using rigid body. Nodes means using one node maybe, and the prescribed motion set is using the set that you have defined before. So node ID, this is the set, and just select move, and then degree of freedom X translation 1 here, and then VID is velocity or acceleration or displacement. I will choose velocity versus time, so this is the default. And the loading curve ID, I have defined it. I have to define this using keyword define curve in keyword. So go to automatically define curve and set the velocity is 1 millimeter per 1 millisecond. So make sure it is start from 0, insert, and then after 1 millisecond I will go to velocity 1 millimeter per millisecond. So just insert it, and until 10 millisecond I also get 1 millimeter per millisecond. Insert, and you define it as velocity of tensile machine and accept it. You can check it later. This is the scale factor. Scale factor means whether on the x positive direction or x negative direction. So this is already good. Plus, yeah, plus it means positive x. ID, just leave it as default, and all of the rest parameter also default. Accept and done. And then that is the boundary condition. And the next step, you have to make it a section. Go to section. This is the definition of the thickness of your shell element, because this is shell element. Yeah, there are many different elements. You 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 can define as SPH, smooth particle hydrodynamics. You also can use beam element, and also shell element, and the last one, no, there is T shell, and also the solid elements. And in here, if you use shell element, you have to define the thickness using section shell here, and define it 3 millimeter, because the specimen says that Tofa defined the thickness is 3 millimeter on the CAD geometry. So I put it 3 millimeter, and also element formulation have to define as advanced as possible, because this element formulation will give you significant results, because the default one sometimes cannot capture the bending, and also the shear, and also the tension very well. So you have to use, I favorably use fully integrated shell element. This is for very fast and high velocity impact. You define it as thickness. Okay, and this is the thickness. The next one, I will define the material properties, because I want to capture from elastic to plastic deformation. I want to use the plastic piecewise linear plasticity 0.24, this one. And you can use from database. Actually, I have been defined it. I have defined it, so I can browse. I used the previous work that I have done. This one. Okay, load, done. And then yeah, this is a mild steel, typically mild steel that people use. I define it. This is the density, this is modulus Young, this is Poisson ratio, this is sigma yield, this is Tangen modulus, and this is failure strain. I define it 0.1. You can define anything up to failure strain. Yeah, this is the typical failure strain in high velocity strain. And this is the copper Simon for mild steel 40 and 5. And also this is the effective plastic strain value. There are 8 points defined here, so you have to put it all the number here. And if you plot it, it is something like this. This is just approximation. This is true stress, true strain. So you have to change your engineering stress strain become true stress, true strain, and done. After you define section and also the material properties, you have to put those parameters on the part. So select the section, define the thickness and the material ID, mild steel, change the name, tensile test, and accept, and done. So now the parameter of boundary condition is set, material properties is also set, and the next one we define the database. Database means you can take the time between in output, so go to the database where it is. Okay, binary plot. This is also for animation. For example, for your animation, you take the result in every 0.1 millisecond. So in 10 millisecond there are 100 frame in your animation. Accept and done. And also I usually use ASCII option. This ASCII option for example global statistic results in energy, and also for reaction force and any other. There are a lot of things here, yeah, something like this, but I usually use global statistics just for looking at the energy. Put the dt interval between output 0.1, the same with the d3 plot. Accept and done. And then after database, you have to define the control here. This is my favorite one, the accuracy. You put it on for global flag for second order objective size update, yeah, something like that. And then I also I also using, termination is mandatory. Termination means your final time. Except then 10 millisecond, I mean. Time step sometimes used for more accurate results, but in this example I'm not using it. And then I forget sometimes because I want to take the strain, so I have to use extend binary here. Extend binary to activate the strain flag. The strain flag must be 1 to activate. Write plastic strain data to delete report and accept and done. And I think that's all the simple modeling, and we go to save it. Just for example here I use a tensile. Okay, save it, and I try to run it. Sometimes if we use DYNA, sometimes we miss the parameters or any other database, for example, or control. It's okay, all people doing that, because the DYNA is not really user friendly, so you have to debugging and also iteration, make some iteration. So now I want to run it using run. You open, make sure this is check, and also number of CPU and CPU like this, and memory is depend on your computer. And this is for toggle to start else then in command prompt. And select your your file in that have been saved. This is this one, and then run it. Sometimes it will get error. It's okay, because uh, in my experience, when I doing the modeling and simulation in DYNA, sometimes you will get error. That's okay. Even as expert as anybody in the world, sometimes get error. It's okay. It is the feedback for us. Oh, this is okay now. This is estimation time 2 hours, and just leave it until done. Sometimes the estimation is not correct. Sometimes only 1 hour. Sometimes, yeah, getting longer, because there is complication, complicated models, large deformation, and unstable results. It will give more time to calculate the results. But uh, in the static or quasi-static, and also stable simulation will get faster. So uh, in the running condition like this, you also can check the result. You not need no need to wait until the end. You can check whether your simulation is going on the track or not. So open the new windows and Control B. This is a shortcut to open up the D3 plot. Control B, and this is your geometry. Okay, D3 plot. Okay, like this. So this is only small, very small deformation. Yeah, you can see it clearly. You can open the fringe to make sure your specimen is moving. Yeah, something like that. Yeah, the next activity, I will wait for yeah, maybe, yeah, 0.5 is very small. Yeah, we can start we can start on how to get the stress strain curve using LS prepose. It's okay. Open the new windows of LS prepose, and then open your key file. Control B. No, not key file. D3 plot. Open it up, and here how I get the stress strain curve. First, click the history here, and click the element, because I want to pick one element as representation, and then select the X stress, of course, because this is the X tensile stress direction. Just plot. So this is the stress. Just save it. Stress. Name it with stress. Save. Done. And in the same element, you take the strain. Yeah, mean X strain is okay. Yeah, mean X strain. Yeah, save it and give the name strain. Okay, after we got the stress and strain, the both file in the time domain. so we have to change in the stress and strain crossly. So we put x as the strain, yeah, in here, x axis strain, and the y axis is stress. Just plot it. Okay, you got the results like this. Yeah, sometimes we want to compare with the material properties that we just input before. We can open the K file, okay, the same, and go to the keyword and material piecewise linear plasticity, and plot at means you plot it, overlay it on the previous graphic, something like this is much higher because 1 millimeter per 1 millisecond is very fast. It means for every 1 millisecond your specimen will deform 1 millimeter. It is so fast. 1 second means 1 meter. So this is the effect of Cooper-Simon constants that you just put in the material properties that inform us the steel material have sensitivity on the strain rate. Yeah, strain rate sensitivity material. Okay, after you wait until the end, you do the same procedure, you will get much longer than this. Yeah, it will goes up like this. I just finished the in here, something like this. You can open your plots. This is, for example, stress strain plot that I have made, something like this. So this is all the procedure of simple tensile test simulation in LS DYNA. Hopefully you will easily follow the simulation step by step that I have give to you. Thank you for now. Thank you for today.